on the first page of the review, this section 7.1 is operations with radical expressions, and the only instructions are to simplify. So the instructions are simple, but knowing when to do what is a little bit complicated based on the initial setup of the problem. So first, if you have a single square root, things you must be aware of are the index of the radical. And I will say that's the number one mistake that I have seen on this test is forgetting to write the index of the radical with your final answer, or forgetting to use that when you are simplifying in the first place. So the index is important. In order to simplify your variable powers, you will take power divided by index. Or you might need to break the power. So what we're going to do is a couple of problems where you can get some practice with these concepts that I'm talking about at the top of this page. So what I want you to do is flip to the very back page where there aren't any problems, and we are going to add a few of our own. So the first problem that I want you to add is the cube root. No, sorry, not cube root. Scratch that. We're just going to do a normal square root of 72 x cubed y z 4. So if I don't have an index explicitly written, what is the index of that radical? 2. It's got to be 2. You don't have to write the index of 2, but you might find it helpful once you start simplifying those variable powers. So if I'm taking the square root, we want to break 72 up into the biggest perfect square factor that we can. If it's not jumping out at you right away, what you can do is look at your squares chart and start dividing by all the perfect squares that are smaller than 72. Can I divide 72 by 64? No. Can I divide 72 by 49? No. You can try that on your calculator. Can we divide 72 by 36? Yes. So we are going to break 72 down into its perfect square factor of 36 and its non-perfect square factor of 2. Now, third block was like, well, what about 9 and 8? What about 9 and 8? The 9 is a perfect square, but 8 you could break down further by taking a perfect square of 4 out of it. So it is important that you simplify the radical fully as much as possible. So from here, we've got x cubed. Now, we've said that the index of this radical is 2 when there isn't one explicitly written. Do I have enough x's to take the square root? Yep, we've got x squared, or at least x squared, so I have enough that I should be able to take out a square root from it. Now, if I try doing power divided by index, we get x to the 3/2. Now, what's kind of confusing is on our second learning target, where we go from radical to exponential form, x to the 3/2 is fine. If I say write this in a rational exponent form, x to the 3/2 wouldn't be a big deal. But when it says simplify, we need to break the power into something I can divide by 2 and whatever is left over. So what's smaller than x cubed that's divisible by 2? X squared. Now, I got a couple emails about this because some students were like, wait, I thought the power had to be a perfect square number. It's not about the power being a perfect square. It's all about being able to evenly divide it by the index. And if you think about it, is x squared a perfect square? It is, because x times x equals x squared. So it's not about the power number being a perfect square. It's all about being divisible by the index. So you don't have to write that index of 2, but you can if you want to. So then what is left over inside a different radical? Just x. So we've got x squared and just x. Now looking at the y's, do I have enough y's to take the square root? Nope, we would need at least y squared, so y is just going to stay underneath the radical. Now with z's, power divided by the index of 2, we don't have to do any breaking up into factors. We just straight up get z squared. And notice that it is not underneath the radical. As soon as I divide the power by the index, we just straight up get z squared on the outside. So power divided by index. And this whole top section that we're going to be doing is for 7.1. And what you'll find is 7.1 is the heftiest section. There's just a lot of different things to cover here. Now from here, we just start simplifying. We break down the perfect square factors that we denoted. So the square root of 36 is 6, and the square root of x squared is x. Is there anything else I can like simplify? Not really. So we bring down the rest of our radical stuff, and all of these terms are joined by multiplication. And that brings us to our last important step of shuffling things around so that all of our coefficients or outside stuff is out in front, and then all of our radical stuff is together behind. So I will have the 6 and the x and the z squared out in front. And then I'm going to mush all that radical stuff together. So 2xy. So when it's a square root, I don't have to write in that index of 2. Just know that it's a 2 when you are taking power divided by index. There's our final answer for this first one. Simplify, simplify, simplify. Before we do the next problem, I want to talk about something with negatives. If I have the square root of -1, what is that equal to? What's the square root of a negative? Going all the way back to the quadratic formula and all that fun stuff. It's I. The fourth root of a negative would also be I. So what about a cube root of a negative? The cube root of a negative is actually equal to -1. It's kind of a tough habit to break just because we haven't seen square roots for so long. It's like, yeah, square roots always come out as an I. But cube roots are different because this is asking what cubed gives me -1. And what cube does give me -1? -1. So -1 times itself 3 times does equal -1. So -1 is a perfect cube, with the cube root being -1. So I would put an important box around this. And the big idea is that odd index radicals like 3, the negatives come directly out, whereas with even index radicals like 2 and 4, the negative would come out as an I. So we're going to go ahead and work through this next problem, which is the cube root of -343 x squared y to the 5th z squared. Now, first big difference with this problem is we've got an index of 3. So I'm going to turn you loose on this one for 1 minute. See how far you can get. And ladies, we're just on the back page of the review, just doing some extra problems. So first, it's a cube root. So how is that negative going to come out of the cube root? As an I or as a negative? As a negative. Then we look at the 343. 343 is a perfect cube, so its cube root is 7. So I take the cube root and it's 7. Now, when I try to do power divided by index for the x, we get 2/3. Do I have enough x's to take the cube root? Nope. We would need at least x cubed to be able to take one x out. So I don't have enough x's. There's no point in trying to do power divided by index or breaking that power. That x squared is going to stay underneath the radical. And I have just made a critical mistake here. Does anybody see what it is? Yes. The index. And if you're like, no, it's fine, Miss Scar, we'll just put it in at the end with our final answer. Horrible, horrible idea. And here's why, folks. If you just say, I'll remember that it's a cube root, and you start trouncing down this way in your work, you'll get to the end and you'll be like, well, hold on, the square root of x squared is just x. And you'll try to simplify it as a square root instead of a cube root. So it is kind of irritating, but you need to include the index with every step of your work. If you forget the indices, that automatically brings you down to a 9.5. We had a big talk about that today with grading those tests, so please make sure that you include the index. And if you're like, it's just a little detail, Ms. Caro, it's like, no, it's a big detail, because if you don't have that 3, you would be able to simplify it further. So cube roots keep the index. So x squared is going to stay under the cube root. Then we've got y to the 5th. Do I have enough y's to be able to take the cube root? What could I break it down into that's divisible by 3? y3. There's my index. And then what would be left over in the other radical? Y squared. So I'm breaking y5 down into y cubed and y squared. It's no different than breaking apart this into something perfect and whatever is left over. It's just here we are relying on the powers to determine what makes it a perfect cube. So now at this point we simplify. I've got that -7 on the outside. The cube root of y cubed, power divided by index, gives me just y. So that's going to be my outside stuff, -7y. And then underneath the radical, we'll have the x squared and the y squared with an index of 3. Don't forget the index. Don't forget the index.
What about the z?
Oh my gosh, we do have a z on the end. Don't forget all the variables too. So z squared, there's also not enough of those to be able to take the cube root of it. So we're going to have z squared, also with that little index of 3 on the outside, and that's going to go under our radical 2. Thank you. So don't forget the index. Don't forget all the variables. Unfortunately, with these ones, there's no way of really checking yourself. So big things, get enough sleep tonight. Make sure you eat a balanced lunch before you come to class, because that's going to help you avoid those little mistakes. And I will do my best to remind you guys, like all those little details. Don't forget your power divided by index. Don't forget your index in your final answer as you are working on the test. So let's go ahead and draw a line. And that concludes my little kind of bit I wanted to do on single radicals. So now we're going to take it up a notch and talk about our radical operations. So flipping back to the first page, what operations do we have with radicals? Adding and subtracting. And when you add and subtract, you want to simplify the radicals first and then combine like radicands. So simplify first, combine like radicands together. Then multiplying. Coefficient times coefficient, or outside stuff times outside stuff. And then radicals times radicals. From helping third block, I'll say that with foiling, a lot of them were confused about what to multiply. So I want you to take a quick look at number 2. How many terms do I have? Is this first parenthesis a binomial or a trinomial? It's a binomial. This is one term with 2 parts. This is one term. And this is one term. And this is one term. So I had some people who were trying to like take the radical as its own separate thing. The radical just kind of comes along for the ride, just like if this was 4x minus 5 times 3y plus 1, since those are different radicals. So yeah, you're only multiplying the 4 and the 3 together, but the variables are still coming along, getting tacked onto those terms. So hopefully that makes sense as far as the multiplying is concerned. And the big thing with multiplying is you want to make sure that you simplify last or simplify at the end. If you're wondering why, sometimes when we multiply our radicals together, we create new perfect square or perfect cube pairs that maybe we can take out. So for example, if I have the square root of x times the square root of x, if we try to simplify the individual radicals, there's nothing we can do. But once I multiply those, we get the square root of x squared, which can be simplified. So a lot of times students will just carry out the multiplication and be like, oh, thank God I'm done. But really, we need to check for simplifying at the end as well. So your biggest check on the first learning target is just make sure you are fully. So folks, our last operation, the bad one, is division. And the thing with division is we don't really divide radicals because we have this rule that says no radicals in the denominator. So instead of actually dividing, our goal with these, or what drives the problem, is we want to try to get rid of any radicals that we have in the downstairs. Now, if you are dividing by a monomial radical, then you just multiply by that radical over itself as the creative form of 1. If you are dividing by a binomial radical, then you multiply by the conjugate over the conjugate as the creative form of 1. And this is just kind of a shorthand for what you guys have in your note packet. So if you need clarification on any of this, you can look at your division stuff and see where these rules are coming from. So we're going to go ahead and flip to the back page, and we're going to see some of these things in action. So let's go ahead and add problem number 3. So 3 cube root of 36xy times 2 cube root of 6x squared y squared. So 3 times the cube root of 36xy times 2 cube root of 6x squared y squared. So how many radicals do we have? 2. So that means we're trying to carry out an operation. These two radicals are joined by multiplication. So I'm going to multiply my coefficients together. 3 times 2 is 6. And then I'm going to multiply my radicals together, making sure I include that index of 3. So 36 times 6 gives me 216. X times x squared gives me x cubed. Y times y squared gives me y cubed. So at this point, I've successfully carried out the operation. But now that I'm down to one radical, we should try to simplify it using our same rules that we did on the problems above. So we look at 216, and then we look at our happy little cube sheet. Is 216 a perfect cube? Yup, and its cube root is 6. So I've got that 6 that's already on the outside, and then I'm going to additional 6 from taking the cube root of 216. Then I've got x cubed. Power divided by index gives me an x on the outside. Power divided by index for the y's gives me a y on the outside. So what operation is joining that coefficient of 6 and the stuff coming out of the radical? All multiplication. So my final answer would just be 36xy. So we multiply, then simplify. So let's see. I'm going to go ahead and do number 4 up here. This one I want you to write parentheses, 4 plus 2 rad 5 times 3 rad 3 plus 4 rad 5. First, we look at the individual square roots. Can I simplify any of them? 5, no perfect square factors. 3, no perfect square factors. 5, no perfect square factors. So there's no simplifying that I can do initially. What drives the problem is the multiplication between these. So I am going to FOIL this by taking this term times this term. So when I multiply those, we multiply the coefficients together. So 4 times 3 is 12. And the radical 3 comes along for the ride. It's no different than if I had 4 times 3x. That would just be 12x. So yeah, that x doesn't really get multiplied. It's just stuck to the 3 that it's multiplying with. Then I multiply my outside terms together. This is all one chunk. So when I take 4 times 4 rad 5, we multiply 4 times 4 to get 16, and the rad 5 tags along. For my inside products, multiplying these together, 2 times 3 is 6. And now I have radical 5 times radical 3. So I can multiply the radicals together. Just like if I had x times x, we'd bump it up to x squared. Radical 5 times radical 3 will give me radical 15. And then for my last product, 2 times 4 is 8. And rad 5 times rad 5 is rad 25. So at this point, I have successfully carried out the operation. Now that I have carried out the operation, are there any radicals we can simplify? 3? No. 5? No. 15? No. Square root of 25? That's gonna be 5. And what will I do with that 8 and that 5? Multiply them to be 40. Now from here, do we have any like terms or any like radicands? No. The 5 and the 15 are close. They both have 5 in them, but not close enough. So don't do any rearranging. Just leave it in the order that you FOILed it. I'm going to be lazy here. Just squeeze that plus 40 in as part of my final answer so I don't have to write all that stuff. So that 4-term nonsense, that is our final answer for number 4. Any questions so far with the simplifying or the multiplying or the adding? Alrighty then, let us draw a line. We're still in 7.1 at this point. As you can see, lots of different types of problems. For this next one, I want you to write 3 over the square root of 48. So operation-wise, we've got division. We do not want to have that radical in the denominator. Now, flipping back to the front side, would you say that we are dividing by a monomial square root or a binomial square root? 48 under the square root, that's just a monomial. Which means we can just multiply the radical over itself as the creative form of 1. However, can we simplify 48 first? Are there any perfect squares we can take out? And if you go, I don't think I would have caught that, Miss Caro, that's okay. You can catch all the simplifying at the end if you want. But remember, your whole goal with this is to simplify as much as possible. The biggest perfect square I can take out of 48 is 16. Someone was like, what about 4, Miss Caro? Well, 4 would leave you with 12 in the other radical, and you could take another 4 out of 12, so that's why 66 square factor. So I'm just going to simplify that radical first. And we get 4 radical 3. Still a monomial because these are joined by multiplication. Just like 4x is a monomial, 4 rad 3 is a monomial. So we want to get rid of that rad 3 in the denominator. So we are going to multiply by that radical as our creative form of 1. Multiplying straight across because that's what we do with fractions. We have 3 rad 3 over 4 rad 9. And if you're like, there's still a radical in the denominator, Mrs. Cairo, not for long because the square root of 9 is 3. And 4 times 3 gives us 12. So 3 rad 3 over 12. And can I simplify that just a little bit further? We can take a 3 out of the top and the bottom. Ooh, and that leaves me with 4.